So now we're going to take what we've learned with derivatives already and do an application of this and say, if I have some function, and if I pick a point on that function, I now know I can find the slope of that line using the derivative. And if I can find the slope of that line, going back to grade 10 math, anytime that you have the slope and a point, and of course, if you're finding the slope at a specific point, you would have that point as well, you can find the equation of that line. So that's our next step. We're going to say, I want to find the equation of that purple line. That's an equation of a tangent line. An equation of a normal line, well, the normal line is just the line perpendicular to the tangent line. So we're going to find that one as well. So going back to grade 10 to remember how to do this, well, what do we know? We need to find a point and a slope in order to find an equation of a line. We're going to get the slope from our derivative. We're going to have the point from our equation, and then you can either use the point slope form, or if you prefer to use y equals mx plus b, you can choose either one of those to find your equation of your line. So let's look at what this would be like. Okay? Find the equation of the tangent to y equals 2x squared plus 3 at x equals 1. Write your answer in y equals mx plus b form. So first of all, you could easily find your derivative. What does your derivative do? It gives you an equation for any tangent slope anywhere. Where in particular do we want to find the slope? We want to find the slope when x is equal to 1. So if you plug in 1 into your tangent formula, that's the slope that you're going to get. So the slope of the tangent line at x equals 1 is going to be 4. Once you've got your slope, in order to find your equation of a line, you always need slope and a point. Well, the point is going to be easy because you know what happens at x equals 1. You've got your regular equation, 2x squared plus 3. You could find your y coordinate quite easily by just plugging in 1 into the original equation. Here, when we plug in 1, we get 5. So our point is 1, 5. We have our slope, and we have our point. And now you have a choice. And I'll show you the slope-intercept form first, and I'll show you y equals mx plus b. But once you have a point and a slope, you have a choice which equation of the line formula you want to use. Okay? First of all, since you haven't done these things for a while, this is the first one that I'm using here in green. Okay? Do you remember learning the point slope formula? Would you have had it in your memory? Yes? Maybe? Okay, good. Just something to connect to. All the point slope formula is your slope formula rearranged. You know how slope is rise over run? Which is y2 minus y1 over x2 minus x1. Can you see that if you divide both sides by the x minus x1, you have your slope formula on the left-hand side? But since you're only using one point, they take the x2 and the y2 out and just change them to x and y. So that's a little bit where that formula comes from. That might help you remember it. Again, I'm kind of curious. I'm not sure if this equation is on your formula sheet or not. But then it's just a matter of rearranging that formula to find your answer. No, I don't see it on your formula sheet. So, or if you like to use y equals mx plus b, in y equals mx plus b, if you have a slope and a point, you can find your b value. Because you know your slope is 4. You know that when x is 1, y is 5. Multiply out, rearrange, solve for b. b will equal 1. So then you can rewrite your equation now with your proper slope and your proper y-intercept. For me personally, when I was going through high school, for me, I heard y equals mx plus b way more than y minus y1 equals mx minus, oh, it just takes longer to say, right? So you'll hear y equals mx plus b, and you'll associate it with lines, at least I did, more often than the point slope. So I tended to use this more often just because I remembered it easier. But both work equally fine and take about the same amount of work. Sometimes one has a tiny advantage over the other, but they're basically the same. So graphically, what's happening? We had our parabola. That's the blue graph there. At 1, 5, there's the tangent line, and now we know the equation of that tangent line. Not only do we know the slope of that tangent line, but we know the equation of that tangent line. So really, all that's new here is taking a little bit of calculus and then applying it to math that we learned in grade 10. Okay? So try the second one on your own. Okay? Check how you did. Did you get your derivative right? Okay, that's the equation of all the tangents. Plug in 4, and you get 20. So your slope is going to be 20, and if you plug 4 back into your original equation, 4, 32 is your point. Once you have a slope and a point, you can plug that in into either equation, and y equals 20x minus 48 is your equation of your tangent line, and there's a picture of what's happening. So now that you've learned this concept, what does the IB like to do? They like to play around with these concepts and try to enhance the difficulty a little bit of these questions. So read over the next one. All right, 2 tangents to the curve, y equals 2x squared at the points where y equals 8. So if we draw a picture of this, we have 2 points, negative 2, 8, and 2, 8. Intersect at the point P. Make a sketch. So here's our sketch. You could find those points, or you could plug in 8 for y and find out where x is and solve and get plus or minus 2. Now that we have that, we can find both of these tangents. Tangent number 1. Well, our derivative is going to be 4x. You can use x equals positive 2 and find the slope of our red graph to be y equals 8x minus 8. Doing the same thing with the second tangent, you get negative 8 as your slope, and it just so happens when you look at those two equations that they share the same y-intercept. So this was a really easy question once you got the two tangent lines. Now, just to remind ourselves of some of the technology that you have, if these two tangent lines were quite different and you wanted to find out where they intersected, you could type 1 into y1 and 1 into y2 and use your graphing calculator to find the intersection point. That would be really quick. But in this case, you could just see it from the equations. You're like, hey, wait a minute. They have the same y-intercept. That's where they intersect. What I really want to focus on this is some of the wording in the equation. So first of all, it says, find the equation of the tangent to, but it doesn't tell you a point for that first part. It says, find the equation of the tangent to f of x, and then it says, and an additional one that's parallel to the tangent at 4, negative 21. Well, when they say find the equation of the tangent to, they're just saying, can you find the general equation of all the tangents? That's their way of just saying, can you find the derivative? But can you see yourself on a test when you see this feeling like, I don't know what to do, because there's not enough information? So the first part is just, can you find the derivative? Then once you've found the derivative, the and one, the additional thing that you want to do is find the one that's parallel to the tangent at 4, negative 21. Well, at 4, negative 21, the slope would be 11. Take a look at our picture here. There we go. Finding the equation at that point we would have y equals 11x minus 65. That's the one exactly at 4, negative 21. So if there was another one over there that has the same slope as 4, negative 21, we would have to figure out what that point would be. In other words, I'm trying to find out, is there anywhere else where the slope is 11? How would you solve that? Well, I could put 11 into my derivative, 3x squared minus 6x minus 13, and solve this quadratic equation. Moving the 11 over, because you solve quadratic equations by making one side 0, you get 3x squared minus 6x minus 24. For factoring purposes, I'd probably factor out a 3. Or I would have cheated, since we already know one of the answers is 4, right? What does the other answer factor have to be to get an 8? It would have to be an x plus 2. Multiply it out and check, and it works. So we would have this point be at negative 2 comma something. Does that make sense? And if I wanted to find the coordinates, the y coordinates on my original graph, I'd have to plug in negative 2 into my original function. Negative 8 minus 12, negative 20, plus 26 would be 6, plus 15, negative 2 comma positive 21. And then you could apply everything and plug that into the equation afterwards. Right, which I have right here. And because we solved our derivative equal to 11, and there was only those two answers, 4 and negative 2, those are the only places that would have that same slope. Right? You know it's going to be a little bit more work as soon as they introduce the variable k. Consider the function f of x, 3x squared minus 5x plus k. Do you like that new notation for functions? No. Guess what? They're changing the notations for combinations next year. Right? In grade 12, you learned this as your combinations notation, right? And then IB switched it to this, right? And in the new curriculum, they're switching it to, oh yeah. Why? Why? What's the point? Why does there need to be 3? I don't know. Apparently, this is more British. And maybe, I don't know, maybe because they decided not to change the curriculum too much. Let's change the notation just so people buy new textbooks. I don't know. Ooh, sneaky. I think I'm going to start inventing my own. I like it. Looks more musical. Doesn't it look like a... Good, yeah. There we go. Ooh, that, I'm pretty, yeah. Has a nicer ring to it. Okay, write down f prime of x. Well, when you do the derivative, the k just disappears. The equation, well, because the derivative of a constant is 0. Okay? Now, the equation of the tangent to the graph of f at x equals p is 7x minus 9. This is a very typical type of question where if you get really good at solving equations of tangent lines, there's steps that you follow, right? You do, just like we did, you find your derivative, then find your slope, then plug in your slope and point into your point-slope form and find your equation. A typical thing that the IB likes to do to see how well you understand something is they take some information away from the top, give you some information in the middle, and see, can you work backwards to get everything original? So at x equals p, which we don't know the value of p, we know that the equation of the tangent line is y equals 7x minus 9. We want to find the value of p. Well, what do we know from y equals 7x minus 9? We know the slope. We know that the slope is 7. If we know that the slope is 7, okay, we can plug that into your derivative and find out that the x value had to be 2 to get a slope of 7. And so if the x value has to be 2 to get a slope of 7, and they're telling it's at x equals p, well then p would have to be 2. You see how we had to kind of work backwards? We had to steal from the equation of the tangent. We have to know, oh, that's in y equals mx plus b form. I can steal the slope from that. And if I can steal the slope from that, I can go to my derivative and plug in my slope, because the derivative is just the slopes of all the tangents. And then I can find the x value. And then if I want to find k, well, I know that on my derivative, or sorry, on my tangent line, when x is 2, y is 5. And that point, 2 comma 5, is on my tangent line, but it's also on my original function. When x is 2, y has to be 5, then you can solve for k and get k is equal to 3. So it's giving you the information in a different order, and now you have to work backwards to find your answers. There's a picture of what's happening.